Hi, my name's Andrew McLaren. I'm going to help you understand the Van't Hoff equation, also why Le Chatelier's principle works the way it does with temperature. It's essentially, if we look at our Gibbs free energy equation, you can see this relationship with G to the negative RT ln K. If you substitute that in and cancel out some of our temperatures here, if you divide everything by temperature, you get this relationship here. So um, S, it's the entropy. Um, it has like a constant effect on K equilibrium, but the change in H very much depends on the temperature. So as temperature kind of goes up or down, that's going to change our K equilibrium's position, but that also depends on the sign of H. So if this is negative or positive, that is going to make that contribute either to making there be a bigger K or a smaller K. If you go ahead and set everything equal to S, you can derive this Van't Hoff equation, which relates how K equilibrium changes with different temperatures. It's kind of a pain to go through, but the big picture is not too bad, and I talked about it in my video on Le Chatelier's principle. Essentially, here, if you have an endothermic reaction, we're talking about something that's endothermic, it's going to have energy coming into the system. So an increase in temperature is increasing the energy, and that causes a shift where we're going to then see the shift coming in where we're like, oh, I've got too much reactant, so I need to get rid of my reactant, make more product, or shift to the right. Um, so if we're talking about something in an equilibrium, if it is endothermic and you add energy, it shifts to the right. If you then were to decrease the energy, it would shift it to the left because it's like you don't have enough reactants in a sense. In other words, you're seeing in this plot of this graph a change that's shifting to a bigger K as that temperature is becoming bigger. I know it's 1 over T, but as 1 over T becomes bigger, then that becomes smaller on this axis. So that's essentially what we're talking about with the Van't Hoff equation. You can talk about the same sort of relationship here with an exothermic reaction. So if we're talking about something that's exothermic, it's got energy that's negative in terms of the change in H. So that means energy is being produced. So if you had an increase of energy there, that's like an increase in temperature, which is going to cause a response of a shift that's going to the left. So it's making more reactants. So we're getting rid of products and making more reactants. In other words, our K is getting smaller. So it's sloped the opposite way on this weird graph with the 1 over T and the ln there. And so it kind of moves that way for an exothermic reaction when we're increasing that temperature. You can see that the slope of this graph is the negative h over r, which if you are careful and you kind of look at this relationship, that is kind of the slope of this. If this is like our x, in the big picture, this is like x, this is m, and this is y. So you've got these two different y positions, you've got these two different temperatures, um, and you've got your slope. That's the main idea with this Van't Hoff factor, and that's why, in terms of the math, we see K equilibrium changing when we are changing the amount of energy that's available to it.